Welcome to the pod Biomanufacturing and Fermentation Technology. In this episode, we translate microbial science, process engineering, and manufacturing realities into insights that scale.
Welcome to this deep dive, where we take your pile of sources and find the critical insights you need. We're not here to read textbooks. We're here to give you the operational fluency that really cuts through the noise. Today, we're plunging into the world of industrial biotechnology, and we're tackling this immense challenge of maintaining sterility at large-scale microbial fermentation. When you're running a massive bioreactor, we're talking thousands of liters. The initial sterilize in place, or SIP, is truly just the starting gun. The real, sustained challenge, as your sources consistently describe it, is something they call sterile boundary management. And here's the immediate surprising takeaway from all this. The dominant risk in modern manufacturing, it's not the catastrophic failure.
Not the big dramatic crash.
Right, not the huge batch turning cloudy overnight. The greater, more insidious problem is what they call hidden contamination dynamics.
Yeah.
We're talking about these low-level subclinical intruders that don't trigger alarms, but can just quietly obliterate 10 to 20% of your product yield. I mean, that's silent destruction.
It is, and it forces us, really by necessity, to treat sterility not as a binary achievement. You know, you're sterile or you're not.
Right.
It's a dynamic system attribute that evolves and often degrades over time, especially under the pressure of continuous operation and these long, extended campaigns.
And what's so fascinating here is the sheer difference in risk between, say, a small lab flask and a 50,000-liter manufacturing vessel.
Oh, it's night and day. Lab runs are short, they're simple. Manufacturing runs expose that sterile boundary to sustained cumulative risk for days, weeks, even months.
So sterility becomes a time-dependent property.
Fundamentally, yes.
And our mission today is to focus precisely on those progressive boundary failures, the ones that escape detection, but that significantly erode metabolic performance and process robustness. We need to find the ghosts that aren't showing up on the petri dishes.
So let's unpack this idea of a dynamic boundary. If sterility is constantly being challenged, what are the primary stressors? The sources are incredibly clear on this. Every single intervention we make is a stress test. Think about it. Inoculation, every single feed addition, anti-foam dosing, repeated sampling, the whole process of linking up the harvest line.
Right.
At a large scale, these operations generate tens to hundreds of physical interactions with that sterile envelope, all in a single batch campaign. Each one is a momentary vulnerability.
And the sources are very specific about what that boundary is.
Yeah.
It's not just the thick metal of the vessel, is it?
No, not at all. The sterile boundary includes all vessel internals, all the inlet and outlet piping right up to, and this is crucial, including the isolation valving and components like spargers or spray devices.
So a crossing is any operation that perturbs that whole defined envelope.
Exactly. And from an engineering standpoint, every one of those crossings applies stress to the critical components. The valves, gaskets, seals, filter housings. The probability of failure for any single event is governed by a whole set of interacting variables.
Okay, can we zoom in on the mechanics of that failure? Because the documents talk about design factors like dead space and seal compression. For someone newer to valve maintenance, what does that specific failure look like in the field?
That's a great question. Let's talk about compression set. So seals and gaskets are made of elastomers, right? Basically rubber or plastic polymers. They're designed to rebound after being squeezed.
Okay.
Compression set is when that material loses its elastic memory. It's like stretching a rubber band so many times it gets tired and just won't snap back into place anymore.
Ah, I see.
So when a frequently actuated diaphragm valve develops that compression set, it creates a microscopic gap when the valve cycles, especially during pressure changes. That gap is your weak point. It's the difference between a hermetic seal and a probabilistically leaky one.
So it's not this huge catastrophic failure where the seal just blows out. It's a micro gap that only sometimes opens under very specific pressure conditions.
Exactly. And you absolutely have to consider the differential pressure. If your reactor is under positive pressure, you're pushing out. But if, say, you're rapidly cooling the vessel or doing a transfer, the pressure drops or even reverses,
creating an inward driving force,
which dramatically increases the ingress risk. You're literally pulling non-sterile ambient air or fluid into that microgap.
And that cumulative risk is what really hurts. As the case studies highlight, if you're in commodity manufacturing with frequent small feeds, you might have hundreds of valve actuations per batch. If just one of those valves gets compression set, you have this statistically leaky boundary that will eventually slowly fail.
It's death by 1,000 paper cuts for the campaign.
This brings us right to the paradox of modern manufacturing. Automation. You'd think it would solve everything.
You would.
Automation generally reduces risk by eliminating inconsistent manual technique, but it introduces failure modes that are often much harder to detect because they're silent and partial.
Right. The problem with automation is this assumption of perfection. An automated valve can fail by incomplete closure or sluggish actuation. If it moves a few milliseconds slower than expected during a pressure cycle, that creates a transient micro-leak pathway.
And you don't get an alarm for that. There's no "my valve is tired" notification.
None at all.
And that ties right into this concept of dead space retention. Automation might make the process more efficient, but if the design of the automated assembly, say, a sampling manifold, has core drainability, where does that little bit of leftover residue go?
That residue sits in the dead space, and that dead space is any volume that can't be fully exposed to, the necessary shear during cleaning or the lethal temperature during sterilization. That residue creates a local microbial niche right on the edge of your sterile boundary.
So it just survives the SEPLP cycle.
It survives, and then when the system cycles again, it gets washed into the next batch. And think about the biggest risk here. The unvalidated branch. An automated sampling assembly might be integrated into the main process, but if a sub-branch of that piping isn't fully integrated into the validated SIP coverage, you have an unsterilized dead leg sitting right inside the assumed sterile zone, just waiting.
That's terrifying, because operators assume the system just handles it all. But okay, let's look at the flip side, manual handling. The sources really emphasize sampling ports as a massive risk area. Why that specific step?
Manual operations introduce variability. It's just human. It's tied to operator technique, fatigue, situational awareness at 3 in the morning.
Of course.
And sampling ports combine everything. Repeated actuation, the physical act of pulling liquid, the aerosol formation that happens when you disconnect, and high-frequency interaction. If an operator's technique is slightly off or they miss one sterilization step on that port, the entire system is vulnerable.
So the defensible position isn't that one method is inherently safer.
Not at all.
Sterility resilience has to emerge from a system designed to be tolerant to the weaknesses of both human variability and these hidden design errors.
Precisely. We see that danger in the hidden leak example they provide. An automated feed valve is outside the validated SAP coverage, but operations assumes it's sterile. Because the leak is probabilistic and the contaminant might grow really slowly, the contamination is sporadic. It only shows up after 3 or 4 days, long after the startup check said everything was fine.
Just a random low-yield tax on every batch.
Exactly.
Okay, here's the pivotal transition. If these subtle engineering failures are creating micro-leaks, those lead directly to the insidious threat of subclinical contamination. This is where the microbiology meets the chemistry in a really destructive way. We established that not all contamination causes that dramatic culture collapse.
Right.
Subclinical contamination is just a small, low-level foreign bug population coexisting with your production strain. It's the ghost in the machine that's just consuming resources.
And the defining, most devastating feature is that the impact is purely metabolic. It's not visual. These low-level contaminants change the chemistry of the batch. They compete for primary substrate. They're stealing the carbon feed intended for your main bug, or they consume overflow metabolites your production strain needs later.
So this fundamentally alters the batch's carbon and redox balance.
Yeah, let's break that down. When a contaminant starts eating substrate, it often produces different byproducts. If it produces more acid, your pH control system has to work harder. If it consumes oxygen and produces CO2 faster, you need more airflow. The whole environment shifts subtly, and that puts stress on your production strain long before the population is detectable.
They increase the oxygen uptake rate, or ROR, which can drive local oxygen limitation, even if the bulk dissolved oxygen, the DO sensor, still reads acceptable.
It's like the system is getting choked, but the main gauge says the air pressure is fine. And let's not forget product integrity. These low-level intruders can secrete enzymes, like proteases, that directly degrade your high-value product, or they can increase the impurity burden, which skyrockets your downstream purification costs. So the yield is down and the quality is compromised.
But if they are so low abundance, why does traditional offline plating fail to catch them?
Because plating is optimized for the organism you want to grow, your production strain. It often fails for low abundance organisms because they're slow growing, or they need specialized media, or their growth conditions are outside your standard incubation parameters.
So we're kind of blind.
Which means we're forced to rely on indirect trend-based signals, especially shifts in the culture's breathing pattern.
And the case study on commercial enzyme production is a perfect example of this.
It is. A contaminant modestly increases the OUR. The operators, following protocol, increase aeration and agitation to hold the DO set point. The DO reading holds steady, sure, but the increased shear and oxidative stress from that higher agitation reduces the specific productivity of the enzyme.
So management diagnoses it as a biology problem, a genetic issue, or a media problem.
When the real driver is a hidden mixed culture causing all this unnecessary stress.
So if we can't see them, we have to learn how to hear them. And that takes us into the diagnostic segment, reading the signals. Boundary failure often leaves these breadcrumbs in the process data hours, even days, before you can detect contamination.
We need to be looking at the non-invasive off-gas analysis signals, oxygen uptake rate, RR, carbon dioxide evolution rate, CER,
Sure.
the respiratory quotient, RQR. We're essentially analyzing the culture's breath.
The sources outline 3 critical mechanistically grounded indicators. The first is substrate uptake, biomass, decoupling.
Right.
Decoupling, that sounds highly technical. What does that actually mean in practical terms?
It means the consumption of carbon you feed is no longer proportionally contributing to your measured biomass, things like cell density. The contaminant is eating the feed, but because it's a non-productive strain, the overall yield just drops. You are literally feeding the ghost in the machine.
Okay, the second one is off-gas variability.
A stable, pure culture should have smooth, predictable off-gas trends under constant conditions. Increased short-term variability, little spikes and dips in OO or sub-OO, that's extremely difficult to explain biologically for a stable, pure culture.
But it makes sense if you have 2 populations competing.
It's highly plausible. It's the sound of the pathogens subtly interrupting the primary strain's respiration.
And the third critical signal is DO control effort drift.
This is a rising controller output. It means you need more airflow, more OO enrichment. Just to maintain the same DO set point, you're working harder to get the same result.
Oh, wait, if we see that rising DO control effort, isn't the simplest, most common explanation just biofouling on the probe itself?
Yeah.
How do we differentiate that from a mixed culture?
That is the essential diagnostic question. Fouling on the DO probe gives you a false low reading, causing the controller to decrease aeration to compensate. A metabolic shift from contamination, an increase in RR, causes the controller to increase aeration effort to compensate for higher demand. We're looking for increased effort to hold the set point, not decreased effort.
So you have to cross-reference this trend against recent boundary crossings, valve logs, things like that.
That's the crucial link. Effective sterility management requires interpreting these metabolic indicators with engineering context. Process data tells you what happened, engineering context tells you how it happened and where it came from.
And what about foam? The sources mention that as well.
Yeah, it's a very non-specific but operationally relevant early warning. Unexplained changes in foam stability or anti-foam demand. It reflects changes in extracellular compounds, potentially secreted by the contaminant, and while it doesn't tell you what the intruder is, it warrants intense scrutiny immediately.
Finally, we have to look at the long game, this campaign-level risk. The sources show that sterility erosion doesn't happen randomly. It concentrates at high-stress boundary locations over multiple campaigns.
And the primary culprit in this long game is thermal cycling. Repeated exposure to the high temperatures of subheat stresses the elastomers and gaskets. They gradually lose that elasticity, which accelerates the compression set we talked about earlier.
And the wear points are shockingly predictable, aren't they?
Oh, always. They are always the frequently actuated diaphragm valves, the sampling assemblies, low-point drains that don't fully empty, and any poorly drainable piping branches. These are the critical weak points where risk accumulates batch after batch.
So campaign-level management has to move beyond just a single batch pass-fail.
It requires comprehensive trending. You need to trend boundary crossing counts per batch, the recurrence of those subtle metabolic anomalies like that rising DO control effort late in the run, and most critically, the maintenance and replacement history for every single boundary critical component.
The industrial example for this is fantastic. Unexplained late-run yield erosion that appears predictably every 6 to 10 batches.
Yeah.
When the facility finally mapped this biological anomaly against their maintenance logs, it correlated exactly with the end of the known seal life cycle on a frequently used feed valve. It was a predictable, campaign-level sterility erosion mechanism, not just random biological noise. So what does this all mean for you, the listener? Sterility preservation is fundamentally an operational discipline that aligns perfectly with reliability engineering. It means making conservative assumptions about human performance fatigue happens, variability happens, and explicitly managing risk accumulation through the hardware itself.
You cannot rely on perfect aseptic technique alone. Proactive inspection and replacement schedules for high-risk components, treating seals and gaskets as consumables with defined life cycles, not permanent fixtures, are absolutely essential for long-term robustness.
So to synthesize, we've reframed sterility. It's not something guaranteed by a successful SIP.
No, it's sustained system integrity that you manage under cumulative risk. That sterile boundary is a defined, sensitive envelope, and every single operational interaction is a controlled stress event.
And the key insight remains that the most costly threat is that subclinical contamination silently distorting metabolic performance. Success requires the fusion of two disciplines, integrating process analytics, those off-gas trends, with engineering context, like the wear patterns on your seals and valves.
But the sources do point to a pretty significant unresolved gap in the industry. It really defines the next frontier of fermentation control.
And for you, the listener, the next deep dive should focus on this. How can systems be developed to provide robust online discrimination between a tree-desired metabolic shift, say the production strain finally hitting peak performance, which is good news, and contamination-driven mixed respiration states, which is the slow, hidden death?
That ability to differentiate between a truly desired biological shift and a pathological one, that defines the next era of industrial process robustness.
Thank you for diving deep with us.
You've been listening to Biomanufacturing and Fermentation Technology with Prasad Ernala. Thank you for joining me. Until next time, keep engineering biology into reliable manufacturing.